Okay. Hi, everyone. And yeah, I guess I'll try to be a bit shorter. So if we have time for questions. Anyway, so yeah, this will be talking about how we categorize emotions on the face. And to start off, you can take a look at these two. What are they? You can continue thinking about that. Well, first of all, how do we perform emotion recognition? And how did people think we do that in the literature? There's two general theories, dimensional and categorical. So when you see a facial feature like furrowed brows or someone like wincing, basically, do you then place these features on some kind of dimensional map where, each point on the map is a particular emotion? Or do you compare this to a categorical representation in your mind, and then you label the category according to whatever combination of features occurs? Well, today I'll be talking about the categorical account, but this is not to discount the dimensional. So why might categories be useful in general, not just for facial recognition or emotion recognition? Well, they organize continuous change, and there's plenty of continuous stuff in the world. So if you think about it like something like attractiveness, or maybe, if you look at animals, there's a lot of variability as well. So there's a lot of four-legged furred animals, and categories give us, kind of easier ways of talking about all this variability and continuous change. So we can say dogs, cats, squirrels, but the same can be true for faces, because there's both a lot of continuous change in facial expression and a lot of variability in expressions. So, how do we know actually that they're also perceptually meaningful and not just a theoretical construct? Well, we know based on, a lot of work that a small physical change can result in a large perceptual change. And one easy way of seeing that is if you consider color as a continuous change in wavelength, we will likely perceive color as discrete unless, maybe if we're interior decorators and we're very good at telling apart these different shades. But usually if you see the rainbow, you will just say Roy G. Biv, not kind of what the exact wavelength of color it is there. And the same can be true for facial expression. So you see a continuous change, and then the expression might change disproportionately to the physical change of the stimulus. And this is what a lot of work has done to kind of show categorical perception of facial expression. You get linear change in blended images that will lead to nonlinear changes in response. So multiple studies have shown this, but I can show kind of three ones that I found that have good examples of this. So this is the Young et al. Megamix, where they use the 6 categories from Ekman faces, and you see the typical S-shaped curves where, as you move kind of towards the edge of the category, so it's definitely, let's say, anger, but then you go across the category boundary, which is the same leap as, let's say, from like 20 to 30%. Now people change it to the other morph. And other studies have done an even closer examination of physical properties to make sure that it's not just some physical change, it's categorical, like in our perception. And this was even done with non-human emotions on the face, where you wouldn't see the categorical perception unless you knew about monkeys' emotions. Otherwise, it would be pretty linear. So, this exists. And our question is more about how will it differ when we give people kind of unlimited options when labeling the face? So usually studies give people options like the ones above, where it's restricted to some amount of categories that, we decide are important. But we also kind of added on top of that the idea that if people freely label this, what will we see? And in order to kind of examine this, we showed ambiguous faces. So physically ambiguous as in 50-50 morphs between category pairs to 74 individuals, and also the original validated unambiguous faces to 71. And then these participants saw 4 ambiguous faces per category pairing. So there was some stimulus variability. And that makes for 60 stimulus in total because 6 categories gives you 15 pairs. And these are some examples from that set. So basically our question was, will they use one of the 2 category labels in the blend, or will they need new emotion labels to describe the face that they see? So one example of this is like this this artist, had some ideas about how the faces would combine into a new emotion, but people may use even more than these. So, okay, we ran this study. So now we have the labels. Now, how do we tell them apart, or how do we see how similar they are? Well, we could just show them to new participants and ask for similarity, but it would take a long time and it's pretty inefficient. And why do that when we have natural language processing methods that deal with exactly this? So one measure that we can use is lint similarity, which is based on information content. And I liked it because it's not probabilistic. It's just like you have the representation and you have an algorithm for computing similarity, and it will always give you the same answer. So you can think of this similarity as being based within a hierarchy of word usage within some corpus. So what this gives you is it gives the word and its meanings, and you can compare it to another word or just one of the meanings. So in my case, I'm only interested in the emotional meaning, so just one specifically. So if I do fear with like sadness, I do the fright meaning, not like, reverence, for example. So I've done this now. Now I have the similarity scores. And, this is still kind of complex enough. So I want to downsample this to 3 dimensions with MDS, and then I cluster this representation. And as you might recall from a previous talk, you can use BIC as a metric for determining kind of the optimal number of clusters or components or whatever you're looking at, because I don't have an a priori idea how many labels people will need to label these faces. So I will just use this metric where you want to minimize it and it penalizes too many clusters because of overfitting. And so what I would expect if it was just the 2 labels is basically 2 clusters, maybe 3 at this elbow. And then after that, you don't really get more information. So the BAC increases again because it gets penalized. But if people use more labels, well, we'll see a lot more optimal clusters. And as you'll see in a second, that is what we see. So, you can look at the purple line or the blue line. These are the ambiguous and the parent category labels. There's a lot more clusters than just 2. But to compare between them, you can look at the optimal number of clusters and see that for ambiguous categories, so that those are the blends of the 2 parent faces. You need pretty much double the amount of clusters to kind of explain the same amount of variance. But you might say, well, of course, there's 2 emotions in that blend. Well, I can just concatenate the labels to the parent expressions, the validated original category expressions, and just have these like paired parent labels. And in that case, you see that you do need about the same number of clusters to kind of give the optimal solution, but the optimal solution for the paired parents is way better. So a BIC difference of like 100 is already significant. This is closer to 1,000. So basically, it looks like the same amount of modes exist in this space, but when you consider parent emotions, which are, well validated and maybe represent better kind of what emotion it is, you might see like maybe tighter clusters around those modes. And this is kind of the next step in this project where we want to uncover this complexity. So one way to visualize this is with these sort of aquarium plots where I can just show you all the words that people use, but I don't want to use, 50 clusters because that won't be very interpretable. So I'll just use 6, like the 6 standard categories. And this is disgust, fear. So you can see like standard category words, kind of towards the left, like anger, fear, sadness, and there's disgust right above in this green cluster. But you can also see completely different words that also cluster together far away from these, disgust, fear related words. So there's a lot here that, it wouldn't make sense if you just considered that you only use 2 labels or maybe 3 as a combination of the two. And one way of kind of starting to get at this complexity is just to look at centroids. So I know the shapes of these clusters, and I can just say, well, which word is the closest to the center? That's what I'll show you next. So, there's a lot of words, but what you can just generally see is that there's not that many words that correspond to kind of the exact word of the pair that you would usually see in like forced choice tasks. And there are some words that are like completely different. So I will highlight the least similar words now. And, some of these emotions, you can look for yourself. Like you would not expect that kind of in a forced choice task. So when people freely label, maybe to them, it looks like that word. So this is like per participant. It's not like some averages or, use the most words possible. It's like every participant might have used one of these words. And when you consider the similarity of all the words in the table to the original category words, this is lower than, well, maybe on par with what's the similarity between any two emotions. So similarity between any two emotions is about 0.5. Similarity between synonyms of emotions like anger and rage might be closer to 0.9. So there's a lot of spread here, but it's still like they're using emotional words. They're just not using only synonyms. And the same is, so this is ambiguous, kind of the blends. The same is true for the parent categories, the original images, where you see words, in this case, like you do see some disgust, anger. So it makes some sense. But on average, you still see this kind of low similarity to the original category words, suggesting that there's more here than just those words, even though, ostensibly we're only using visual features from those categories. So what this really means is, categorical perception of emotions is pretty complex, maybe more so than we continue to think in the literature. And one thing to note here is there are differences in the solutions in terms of BAC and kind of the various explained, but at least the centroid approach, like the labels similar to centroids, they're likely distributed in a similar manner because of the similarity kind of to the original category. But you should know that I could have missed like 2 modes being far away from one another as opposed to, one average kind of mode in between. So I will need to look further in to see the exact complexity of these labels. And, as I've said before, the large number of ideal clusters shows that people will need more than 2 or 6 modes to describe, what are ostensibly just 2 category blends or, the 6 classic categories. And this is not particularly new. I've seen work from 2020, for example, I cited in this presentation that show up to like 27 categories and, also like 12 dimensions that you need to go between them. So this is, to me, like the next step within this kind of sub cluster of the literature where we know there's complexity. So we just need to examine it and see like how emotions change or like where they're located in the mental space. And similar to the last talker, I have made this available on OSF if you want to look at the underlying submission for this. So, if you think you can do a better job or you have some more ideas about this data set, you're free to use it. And with that, I think I'll end my talk and just give some acknowledgements to my advisor, Ben Ballas, who's in Fargo, where it's pretty hot, and my research assistants at the time, Jessica and Faith, who helped me with data collection and analysis. So thank you.